Hi, hello everybody, good night. We are live streaming here tonight in English. So we are live streaming from the Gran Telescopio Canarias. So we welcome you to the largest optical infrared telescope in the world. And we hope you ask us through our chat. So you're free to ask us everything about about astronomy tonight and Gran Telescopio Canarias. So here we have Romano Corradi. Hello, Romano.
Hello, Elena, and good evening to everybody.
Okay, so
or good evening, or better said, you never know. Good evening, good morning, or good afternoon, whatever it applies. Yes. Yeah.
Because we also have many people from United States. I hope so. So will be good afternoon. So okay, right. So tonight, hello everybody. Will be mostly in English, right? So we want to open our doors to all the English people, not only English, of course, but for all the people who maybe do not understand Spanish. So I think it's a good opportunity to all of you to follow us and interact with us through our chat, live chat. Right, so tonight we have a lot of good news, a lot of important things to show you, right?
It has been a very exciting week, I would say. Not only the first picture of a black hole, everybody has seen it, and we will talk about that later. We have a very special guest, Phil Charles, an astronomer who first discovered a black hole in 1992. So he knows everything about black holes. He will answer any question you may have. But before getting into the news from the GTC or Grantecan and the news of the week, I think it is the first time we are here in English, no? And not everybody knows about the Grantecan. I think it's important, first of all, to locate us in the planet.
Right.
Yeah?
Okay, so we are a little island in the middle of the ocean, Atlantic Ocean. So we are on La Palma. Here we are on our shoulders. You can see our bags. Gran Telescopio Canarias. So that's it. You can see the dome.
La Palma. La Palma is in the Canary Islands. Not everybody knows that. It's one of the smallest and the greenest islands. It's just a beautiful island. It's just the only adjective is beautiful island. Is basically a mountain that comes up from the bottom of the ocean and goes up to 2,400 meters above the sea level, but then there is another 4,000 meters below the sea level. So it's one of the highest mountains in the world, and in fact it's the island which is probably
the steepest island.
The steepest island in there, and it's beautiful because it's a variety of climates. It's green. It's a green island. You have beaches, but you also have a lot of forests. It's a paradise for hikers. It's beautiful nature, not too many people. And one very important thing, we have very special conditions to study the universe for several reasons. First of all, because there is a mountain, and here there's a phenomenon that below a certain height it can be cloudy and rainy, but above is always, say 75% of time is clear. Second reason are the winds, the trade winds, that come from northeast usually, and they clean the atmosphere. It's very nice atmosphere to look at the stars because you see stars in a very sharp way. And the third thing is light pollution, which is not existent here.
Yes.
There are not many people living in La Palma, about 60,000, 70,000 people. But in addition, there is a law that protects the sky, which is one of the best things we can have. We look at the sky at night and we can see the Milky Way, and not many people in the world can say that.
Actually, we are very proud of the sky law, and we celebrated the 30th anniversary last year because it was signed in 1988. So 30 years with this important law.
Yeah. There is one thing tonight, you know. At 10, there will be a blackout done on purpose over the whole island in order to allow people to see stars even better from the cities. There will be a lot of events where people go with their small telescope, and you can see from the middle of a small city, you can see really stars as if you're here up on the mountain.
That's right. It's 10 o'clock in the Canary Island time, so universal time +1, so it's
Okay, so let's continue, right. if you allow me, to tell you a little about the telescope. I mean, Elena said it's the largest optical telescope in the world.
Right.
Can we put a picture from
yes,
inside?
Oh, from inside, of course. So you can see, you can see the telescope, the big one. Okay, so this is the telescope. Let me take the pointer. Basically, so here you don't see it because it's so reflective. But this is the primary mirror, which is made of 36 hexagons. We will talk about that, which is the most important thing of the telescope, because it's our lens. Okay, instead of a lens, we have a mirror, because the mirror works as a lens if it has the proper shape. And this is the largest of the world. So sometimes people ask me, what does it mean? Why do you need to make very big telescope? It's very simple. We need to collect as much light as possible in order to see objects in the universe which are extremely faint. How faint, people ask. So I prepared just a slide that compares what the Gran Telescopio GTC can do compared to what the human eye can do. Human eye is a beautiful machine. I mean, the combination of our eye, which is lenses and a sensor, with the brain that processes most of the information, is a fantastic machine. I think it would be really difficult to do something better, but still, it's limited because it's a small size. Okay, so the amount of photons or particle of light that go through the pupil of our eye is limited. What you want to make a pupil as big as possible in order to collect as many photons as possible, in order to be able to reach very faint targets. So if you go to this slide, don't want to spend too much time, but we could spend a lot of time. Here, I don't know if you can read it, but there is a comparison between some properties of the human eye and the Gran Telescopio telescope. So the first, most important thing is the aperture, ability to collect light. So our pupil opens and closes depending on the light. At maximum, it opens to 8-9 millimeter. Okay. The telescope, the aperture is the aperture of the mirror, 10.4 meters. And as the aperture, I mean the area goes with the square or everything, just for the aperture, the telescope gains by a factor of 1 million to compare to the eye. So we are able, in principle, to see objects which are 1 million fainter than what the eye is able to see. First thing. Second thing, integration time. You know, our eye integrates every 15 times per second, because we don't take pictures, we see videos with your eyes. So this is limited. The amount of photons that end on the sensor, which is the retina, in 1/15 of a second is limited. With a telescope, like with a normal photographic camera, you can integrate as long as you want. This is important. The telescope here with the GTC, sometimes we take pictures that takes 10 hours to get a picture, or even there is a program that is asking to observe, to integrate in the same region of the sky for more than 100 hours. So if the ability of integrating for a long time compared to the eye, makes the GTC to gain by a factor of another 5 million. Okay, if you multiply 1 million by 5 million, you have 5 million, 5 trillions. I think so. Yes.
So this is one of the main points. We make big telescopes in order to get as far as we can, and actually we, in principle, are able to get to the limit of the universe, or better said, when we look far away, we go back in time.
Yeah, right.
So we are able
using a time
to
machine.
get to the very beginning of the universe, when the first stars and galaxies were formed. And this is when luminous matter started to appear, which is about 150 million after the Big Bang. So, but then there is another important quality, and then we move to see a little bit more the telescope, is the ability to the acuity of the telescope compared to the eye. So the resolution, the ability to separate two dots a certain distance.
Yeah.
Okay. In the case of the eye is 1 arc-minute, which is 1/60th of a degree. In the case of GTC, Gran Tecan, it depends on the wavelength, but can be up to, say, theoretically up to 5,000 times better.
Yeah.
So not only we see fainter, but also we see sharper than the eye.
Right, and sorry,
Yeah.
Romano, they are asking, what is the visual limit magnitude in Rocca de los Muchachos?
Good question.
Yeah.
Well, I must be
visual
around, say,
limit.
6. As I'm not, I have glasses. I'm not very good with that. I never tested myself the photometric limit of the eye. But
Yeah.
should be something like that. Yeah.
Yes, could be.
Yeah.
Of course, if you use a amateur telescope,
No, but this is visual.
it's a
This is
visual
the
limit.
the question. So it's probably around 6. Actually,
Yeah.
a certain point, as the resolution of the eye is on 1 arc-minute, it doesn't really matter if the stars are sharp as here in La Palma or in another place. So something like that, around
Yeah.
6. While with Gran Tecan, we were able, I will show you an image. Let me look for that here. We got down, for people who know about the definition of magnitude in astronomy, magnitude 31.5 magnitude per square arc second,
yeah.
which is, again, let me calculate that. 31 minus 6 is 25. 25 magnitudes is 10 orders of magnitude. 10 billion times deeper than what the eye could be able to see in this image. In this image,
Yeah.
you see a galaxy, which is not that far away, only 50,
It's
50.
400 million light years.
Well, it can be 400, yes. But the important thing is not the distance, because you can observe galaxies which are much fainter. You look here, for instance, this is
Yes.
probably not stars, but far away galaxies. The important thing is that we were able to see in the neighbors of the galaxy, this area, yeah, where far away from the center of the galaxy, where there is the black hole, as in most of the
Yeah.
galaxies, there are still stars, and we want to understand when at a certain point the galaxy ends. So this is what the aim of this observation. So the only thing that the eye gains with respect to this telescope is the field of view. Of course, telescope has a lot of magnification. Actually, the focal length of this telescope is 170 meters. So it's like as you have an objective of your reflex camera, but with a focal length of over 170 meters. Yeah, and so for this reason, we see only a tiny portion of the sky, while our eyes is able to see a bigger portion. Even if really the focused portion that the eye can see is very small, is about 2 degrees. Okay, so let's continue. That was just to justify why we are here, why we have built this fantastic machine, the Gran Tecan, which is mainly a Spanish installation with the participation also University of Florida, Mexico, but as science, I mean, is a collaborative effort. And generally, the research groups are made of people or scientists from very different places in the planet. So actually, many people in the Earth have been able to use the GTC.
Yes, right. Yeah, so actually...
By the way, I see that Isabel is there. I have a present for Isabel. La Palma. You will enjoy that, Isabel. Here it is.
It's a...
Well, closer. Here it is. This is a banana from, put it in big.
From La Palma, yeah, of course.
There we are. This is a banana. This is a banana from La Palma.
Oh, it's slightly green. Slightly green.
Because of the chroma, looks transparent. Yeah, but actually the main production, agricultural production of La Palma is really bananas. So we really enjoy that.
Yeah, we are surrounded by bananas. Not up here, of course, because bananas plantation cannot live up here, 2,400 meters, but close to the sea level, right? So. Good. Yes, Romano.
Let's continue see the telescope. I mean, for this is a project that we started in Spanish. Now we do in English, and we try to reach as many people as we can. The idea is to open the doors of this facility at night at people, because it's very difficult. Actually, it's impossible to come up here at night, not only because we are in a remote island, also because the scientists have to work during the night, so the access to the telescope is not allowed. So the idea was to make a web page, where we put several cameras. People can see, for instance, why don't we put the...
Yeah, right, that's
we have an outside camera. You can see we are close to the sunset now. Yeah.
And we can also play with the azimuth.
Actually, leave it rotate.
Oh, rotate, okay.
Yeah. So you see this side, the sun is about to set today, so we are about to start our observations. And this is a no sky camera that when there is no moon, which is unfortunately is not the case today, you can really see stars and the Milky Way in a very very well. This is a reflex. A reflection, I think. And anyway, then we have a camera inside the dome. So this is our telescope. We just opened the dome before the sunset in order to allow the dome to ventilate and the telescope to reach the same temperature as outside. Otherwise, some turbulence will be caused by the difference of temperature between the structure of the telescope and the air.
Right.
So the telescope is open. You see from the bottom here, this is a view from the bottom.
Yeah, that's...
Yeah, this is the shutter that we open, so the telescope is looking outside there. I will show you some animation later. But then you have more cameras. We have cameras in the control room.
Yes, we have control room, so we can have a look at what astronomers are doing, and we can speak with them, of course. Also another camera here, and then later we are going to talk with them. So these are our astronomer and operator. Okay. And also we have a camera, but we are going to show it, or maybe now, of course, it's totally dark because sky is not dark enough, but it's a very good camera mounted on the back of the mirror, secondary mirror, called M2. So this camera sees what the primary mirror sees. Right, Romano? So it's just a lens, it's a 50 millimeters lens, 55 I think, and it's a very good camera to capture a big portion of sky. So now, of course, it's not showing...
It's not dark enough, we will see later. Tonight we have a strong moon, and that means that the moon actually disturbs the observations, especially in the kind of light that our eyes are able to see, which we call visible light. Yeah? But if you want to observe in another wavelength, which is the infrared, still you can do it very well with a big moon as we have today.
Yeah, I think then we can talk with our astronomer, and so he can explain what we are going to look tonight.
Yeah, we'll see later. Continue just with a description of the telescope.
Yeah.
And we spend a few minutes talking about the mirrors, okay, which is really the important thing of the telescope. Yeah. So if the telescope contains a main mirror, which is you can show it.
Yeah. So here.
Just play it. So this is just an animation of the primary mirror of the telescope. You can see it's not a monolithic mirror. It's made of 36 hexagonal segments. And this is why it's virtually impossible to make a single mirror, one piece, more than 8 meters.
Yeah.
So all the largest, actually our telescope and other 2 telescopes in Hawaii, the Keck telescopes, and all the telescopes of the future, the monster that will come in less than 10 years, they are all made with the segmented mirrors. So every segment is an hexagon, and every hexagon has to be maintained aligned with the other ones in order to maintain the perfect shape, which is a
hyperbolic,
a hyperbolic one, which basically collects the lights from the universe and then collect it in some focus.
Yeah.
So here is speaking about this mirror. I show you. They are pretty big. They are 2 meters each. They are made of a special material, which is a vitroceramic. It's similar to the vitroceramic you have in the kitchen, but it's even more robust, because the important thing that with the change of temperature, it does not change the size. So it's very stable against any change of temperature, which is fundamental to maintain always the perfect shape for the mirror. So this is really the most important piece of the telescope. However, the mirror, let's go and move to another thing. This is an animation, this actually is a 3D model of the telescope that, by the way, was done with Touch Designer. So is everything here, as we have the community of people from Touch Designer looking, all the controls of this streaming are done with Touch Designer, which is a fantastic software that we have adopted as soon as we knew about its existence. It's a fantastic one. So here, let me simulate. Don't disappear. Put the dome again. I open it.
Yeah.
Okay. As we do, about 1 hour before the sunset, we open the dome. Actually, here it's much faster. It takes several minutes to open the dome because it's huge. You have to think that this shutter that has opened is as big as a tennis court.
It's 41 meters to the top.
So this is the size. So if as is a model, I can remove the dome, and here inside you have really the telescope. Let me zoom a little bit. Okay, let me turn it. The telescope is, in order to point in the sky, turns in this way. It's called azimuth, and also is able to change its elevation. So it's the combination of the two movements that allows the telescope to point a star in the sky and then to follow its movement, which is of course due to the rotation of the Earth.
Yes.
So if we zoom a little bit, here you have the primary mirror. You see, the light enters from the sky, is reflected by the mirror, and is focused toward this region. Okay, we could put our camera there, but it's not convenient to have a camera there, so we decided to put a secondary mirror that reflects the light back down. Okay.
Yeah,
and this
so
secondary mirror is also
we can show it.
Yeah. Okay, so it's reflected. Then you have a secondary mirror. Light goes down. You can leave it. Let it play.
Okay.
Yeah?
So
Goes down, is reflected. There is secondary mirror. Then there is a tertiary mirror, which finally sends the lights to the focal stations where we put the instruments. Okay. Actually, there is another one, another image here, another video.
we can see
It's this one.
M3. Yes.
This is the third mirror, which is flat. So you have an idea of the telescope. Again.
Yeah, the third
There
mirror
it
is inside.
The structure just to maintain all the optics. The telescope moves, and then the light enters, reflected, and goes to the focal station. So that's very important, because when you buy a reflex camera, usually you buy the body, and you change the lens.
Yeah.
No, here we have the lens.
You cannot do that.
We have the lens, and we change the body.
Yeah.
So we have several places in the telescope. Yeah, here, 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 and here, even there, where we can put the instruments. And that's very important because in astronomy, we only have light. So the only thing we have from the universe is light. It's a nice science.
Photons,
we cannot go and touch and destroy. Well, in the solar system you can do these kind of things, but not outside. So really we have to use our brain, which is the physics, the law of physics, in order to understand for the few photons, for the few particles of light that we receive, all the properties of a galaxy that is maybe 100 million light years away. So in order to do that, we have very sophisticated instruments, which allow to study the light in all their wavelengths. They are able to observe in the visible light, in the infrared. They're able to observe in the thermal infrared as well. And also they're able to split the light into all the colors, we call it spectroscopy, in order to deduce all the conditions of the matter that has been emitting the light. Can be gas, can be dust, can be reflected light, can be from a star, can be from a very cool environment. So all this information is contained in the few photons that we have to analyze in as much details as we can in order to understand how the universe works.
The composition of a star, for example, at its age and
yes.
everything. Yeah.
So again, we could spend a lot of time speaking about GTC. Astronomy is nice. It's a compendium of all the different kind of technologies, because here, of course, we have fantastic optics, but also we have mechanics. Actually, this structure that I'm rotating now weighs 400 tons.
Yeah.
Yeah. The only reason of these 400 tons is to point in the sky and maintaining the perfect shapes of the mirror in order to form an image of the astronomical object as sharp as possible and as deep as possible in the focal station. So we join the big tons, many hundred tons, and the small, which is the precision we need to align the different segments, which is millions of a millimeter.
Yes,
of a millimeter.
Right. It's also very complicated, because you have to maintain 400 tones perfectly functioning, but if we remove brakes, we can actually push the telescope by hand. So it's a jewel of the engineering, so my point of view. Right, so here we have a lot of people watching now. Come on, so ask questions, don't be shy. You can use our live chat.
Actually, there is a question about food.
Yeah.
It was answered by by Dave, who
answered.
We have here at the top of the mountain, there are several, a good number of telescopes. I would say something between 10 and 20 telescopes. So different scientists at night which are working in different telescopes. We have a sort of hotel, call it residencia, where we can sleep during the day, of course. Yeah. And then we can, of course, eat.
Yeah. So, but we do not eat only bananas, of course.
No, but mostly bananas, yeah.
Right. Okay, so Romano, maybe we can show, you were talking before about the foci. We have 7 foci stations here. The Cassegrain is the main one, and then the 2 Nashmith 1 and 2, and the 4 green ones. Now we are mounting the latest instrument, Canary Cam, but it is not yet.
Well, next week, it will be next week.
Yeah.
Actually, now we have on one side here Osiris, which looks as an instrument able to take images and spectroscopy in the visible light. On the other side, we have Emir, which does the same, but in the near infrared light.
Yeah, we have a picture, I think.
Yes, we'll see it later, because when we will show the important results that Gran Tecan has obtained in the last couple of weeks, we'll talk also a little bit about the instrumentation. So, I was talking mechanics, optics, software, of course, is fundamental, because the movement has to be very precise, and the 2 movements are combined by a control software. And then electronics, of course, very sophisticated, but also very important kind of discipline is cryogeny.
Cryogeny, yes.
Okay, because in order, we have detectors which are very sensitive to light. Actually, they detect out of 10 photons, 9 photons, or even 10, depending on the wavelength. But in order to do that, and to remove the spurious noise of the detector, the electronics of the detector itself, you have to cool down as much as possible. This is in the visible light. In the infrared, we have an additional problem, because the infrared, we are catching emission that's not only from the sky, but also from the environment.
Yeah, right.
So you have to isolate the instrument from the environment as much as possible. And actually, we have an instrument which works, is a thermal camera, basically works at 10 micron. that needs to be isolated by itself. Okay, so really it works at a temperature which is very low, 4 degrees above the absolute zero. So which is
around
269 degrees below zero Celsius.
Yes.
Celsius. I don't know Fahrenheit, but you certainly know. So cryogeny is also very important. We cool instruments with different methods. In some cases with the liquid nitrogen, but when we really want to go to very low temperatures, we have to use helium.
Yes, right. So, helium is more efficient.
So here there is not only a combination of optics and air, but also a number of pipes that bring coolant up and down from compressors to instrument. Water has to be cooled as well in order to cool down the electronic racks. And then we have the electrical supply, and etc., etc., etc. It's really a complex machine that, in addition, has to work 36.5 days a year.
24/7. Yes, at night, of course, but also during the day, all our engineers and other people, technicians, have to work the telescope to fix it in case we have some problems. So 24/7, actually.
So what we can do now is to move to the first topic of the night, which is perhaps the most important topic of the year, which is the discovery that everybody has seen, or not the discovery, but the fact that astronomers have been able to take the first picture of a black hole. Okay, speak properly of the shadow of a black hole. So in order to do that, what I would do is perhaps we call Phil Charles.
Yeah.
Yeah.
I'd like to show the picture.
Of course.
That's it.
Everybody have seen it.
Yes, yes.
The best to talk about it is to really call. We have a chat.
Yes, right.
With Phil. Let's
okay, so we have him here. So we can. Okay.
Hello, Romano. Hi. I can indeed. I've been watching your streaming so far and enjoying it very much. I'm delighted to help, Romano. Indeed, in fact, this year is exactly 30 years since we had what was then the biggest telescope on La Palma, the William Herschel telescope. And in that year, that's when we discovered the mass of what is still perhaps the best binary black hole system in our galaxy. And so, what is really exciting about the discovery this week is that all these years we have been going on measuring masses of black holes. These are mostly the ones that we've done accurately have been in binary systems, pairs of stars in our galaxy that we can study in some detail. And we believe. I can hear you fine. I can hear you fine, so I'm. So is the problem that they can't? Yep.
We can't hear him. We cannot hear him. We can hear you, but not him
Oh,
or her.
that interesting. Apparently, the YouTube can hear me, but not you two. Okay. Yeah.
Yes, we are
No,
back
no,
now.
look at that.
Okay.
Now it is.
Yes.
It was off.
Yeah, yeah. So I think now,
We can try again.
yes, we can try again. Okay, so we call Phil again. Good. Just a second, and we try again.
Phil, you can connect again if you like. In the meanwhile, we have put.
Yes.
I think now people can hear us. Yeah, we have put on the screen.
Yes. Now I
Yeah.
think. Yeah.
On the
Okay.
screen, we put the paper from 1992 by Jorge Casares, who is an astrophysicist from the Instituto Astrofísica de Canarias, from the nearby island of Tenerife, and by Phil, yeah, where really they found the first empirical evidence of the existence of a black hole. Yeah. So as soon as Phil comes back,
Yes. Now I think he can call us in a
we
few
continue
seconds.
talking about that.
Yeah, yeah, yeah.
Yeah.
But I think, yes, Phil, we have to wait 30 seconds because of the delay of the transmission. So I think he will call us right now.
Actually, he will comment about that better than I do. But here is the important figure. Let me use a pencil here to show. This is really the important figure, which is basically this kind of curve is the variation of the velocity in its orbit of a companion
Yeah.
or something that was not seen. Okay.
Right.
So measuring the velocity, the orbital velocity, you're able to measure the mass of the other body. And by measuring the velocity of a companion star, Phil and Jorge were able to determine that in the center there was an object, invisible object with a mass that for the mass it must have been a black hole. Yeah. Something you can do, perhaps just call him. Is it?
Yes, because I don't know why Phil.
Put Phil there. Phila.
Yes, we are trying to. Don't you remember better than me? Okay.
We are trying to call.
Yeah, we are
Phil
trying
again.
to call it back.
If it doesn't work, we try later. Yeah. In the meanwhile, why we
Yeah.
we
While
solve
we are
this little
waiting.
problem? Why don't you put a video of the GTC?
Yes, right.
Yeah, so we can. in the meanwhile
Right.
to work together.
So we have a lot of videos about GTC, but I think it's a good one. This one, so we can watch now the video, and in the meantime. Okay, now you're live again.
Hi, Elena.
Hi,
Can you
hi,
hear?
Phil. Sorry about the technical problem. Can you hear us? I think so now. I think it's
I,
okay.
I can hear you
Yeah.
fine.
Okay. Good. Yeah, we apologies for the this technical problem. Sometimes it happens.
That's
We are
fine, that's
live,
okay.
so
That's live. Look, Phil. We have put on the background image. We have put the title, where actually a cut of your paper in Nature, 1992.
okay.
Yeah?
Now
You'll probably be
you're live
able to
again.
see it in a few seconds.
Hi, Phil.
Hi. Hi.
Yeah, you have to feel, you have to take your sound.
To mute.
I've just done that.
Okay, perfect.
Good.
So, but if you can see, probably you can already see the piece of your paper. Yeah.
Yeah.
And what we think is an important figure, not the radial velocity curve.
Oh, absolutely. And in fact, as people will notice, that this is a paper that was done, almost 30 years ago with my then Spanish graduate student, now one of your most senior astronomy professors in Spain and major users of Gran Telescopio, Jorge Casares. And we used the William Herschel telescope to observe the motion of the companion to the black hole. And that's how, by watching its motion, as you pointed out, that's how we saw we were able to measure the mass of the object we couldn't see. Now, this is the same technique that's been used now about a dozen times or so in our galaxy, and we have very strong evidence that these are all black hole systems. But of course, in a way, it is indirect because we know there's a large mass there, and it's putting out a huge amount of energy, and the constraints on its size means that there's no choice for it to be a black hole. But we'd always dreamed that one day we would be able to image the area around a black hole. Now, we were doing this in the optical and in the X-ray, and the resolution on the sky that's needed to actually see what's going on is utterly beyond our technology. But the enormous advances in radio astronomy, in particular in submillimeter, in recent years, led to the formation of this collaboration who used telescopes from around the world to combine them to make a telescope with an effective diameter the size of our planet. Finally, we would get a resolution which, as you will have seen, is about 40 micro arc seconds, an incredibly tiny angle. It's such a tiny angle. I love the analogy. It would be like sitting in London and reading a newspaper in New York. That's the kind of angular resolution that you would need. The radio could do it, and that's what this collaboration, which was put together, observed this object M87, which is not anything like the black holes that we're observing in our own galaxy, but M87 is an enormous distance away. It's about 50 million light years away. But we believe, based on observations of its extraordinary properties, which have been going on for the last 100 years, that it contains something much, much bigger than the binary black holes we see in our galaxy. And this one had a mass estimated something between a few and 10 billion solar masses.
Okay.
That is the image that the radio astronomers have just released this week from their Event Horizon telescope, which I think is spectacular because it is finally has the geometry and properties that we would expect for an object of that size. So we can finally actually see it. We can't do that as I said, in X-rays and optical, but the radio holds that possibility.
Phil, later we will comment more on the black hole in M87, but just to make the link, the complete link. So you discovered the first black hole, which is a stellar black hole, 1992. How many stellar black holes are known today?
20.
20. So the progress goes low.
Yeah, we only find them when they outburst in X-rays, and it's a particular type of X-ray source which we call X-ray transients, because it's only when these transients turn off that we have the opportunity to study the normal star that goes around the black hole. During the X-ray outburst, we can't see it; it's completely swamped by the heating from the X-rays. But when the transient's not there, we can see the donor star and observe its motion. That's how we measure the masses. And we've been doing them at a rate on average of no more than about one a year. You're absolutely right. This is difficult and challenging observations, needing the world's largest telescopes as well.
Yeah, this is the point I wanted to make. It's really a difficult job, to find a black hole by the nature itself of the black hole. How many black holes are supposed to exist in the galaxy? Stellar black holes.
That's a very interesting question. And it's a very controversial one, because it means understanding the population that these sources are drawn from. And we've only been doing X-ray astronomy for 50 years, but we believe it's several thousand of this type of object that we. And in fact, Jorge is developing a really innovative way of trying to find them without X-rays, which we very much hope will be successful. But it is a very difficult observational project.
Okay. So which is the mass of a stellar black hole? So a single or a binary star, which is the maximum mass can produce a black hole?
The measurements that we've done over the last 30 years, they are all in the range about 7 or 8 times the mass of the sun, up to about the heaviest was about 15 times the mass of the sun. And the one that we discovered 30 years ago has a mass of about 11 or 12 solar masses.
Which is the size of those black holes?
The physical size.
Yes.
Well, here's the question is, what do you mean by the physical size? Of course, you're talking about the event horizon which has just been imaged. So you're talking about something that is only about 20 or 30 kilometers across, something the size of a city, something the size of Tenerife, for instance. And yet contained within that volume is this incredible mass of 10 or 12 times the mass of our sun. These are incredible densities.
And so we're picking of stellar black holes of masses about a bit less, 10 solar masses, say.
Right.
Then you have been introducing the 6 billion solar masses black hole in the center of M87. Yeah, okay. What is in the middle between these two extremes?
Well, that's another really good question, because the really big ones were discovered in the form of quasars in the 1960s. That was one of the great events I can remember when I was a student at school. And it didn't take too long before this extraordinary idea that these were the most luminous objects known in the universe, and the only way you could power them and make them variable as well is to make them accreting supermassive black holes. And so they were always talking about masses between like 100 million and 10 billion solar masses. And over last 50 years, using observations with both in the radio and in the optical with Hubble Space Telescope, we found all kinds of ways of tying down those masses. And as this has happened, over this long time scale, it's become clear that almost all galaxies have a very massive black hole at its center. Many millions up to billions, and this is actually linked, we believe, to the way galaxies actually form. Now, that's why you're probably aware that the Event Horizon Telescope people were the two best objects to look at are our nearest supermassive black hole, which is of a quasar type, which is M87. And the other, of course, is the center of our own galaxy, which is much closer. It is a mere 25,000 light years away. And that is the second target that the Event Horizon Telescope has obtained data on. And they are working on that now. And we are hoping for something very interesting out of what our own center looks like. But there's one big difference between the supermassive black hole in the center of our own galaxy and M87. M87 is what we call is active now. It's a very powerful source of X-rays and radio. Our galaxy isn't. It's in a quiescent phase. We've measured its mass by looking at the way red giant stars, which have been found orbiting the very center of the Milky Way, with fabulous high-resolution near-infrared images from Chile and Hawaii. Teams from the US and Germany have been following those motions, and we see stars actually orbiting around the core, and that gives us a direct measurement of the mass of the object they're going around. And it's about 4 million times the mass of the sun.
Phil, while you were speaking, we put in fact a video.
Yes, I see it on there now. That's exactly it. And you can see the closer you look to the center, the faster they are moving. And those velocities, these images were put together over about 10 years. And the shortest period, one in a highly eccentric orbit, we believe that orbit is going to decay and the star will literally be torn apart. And the black hole that you can obviously see, there's absolutely nothing coming from the center there, will be accreting matter and will suddenly turn on and be very bright in the optical, radio, and X-rays for a short period. And this is how quasars behave. They are active for sometimes months or years even, and then they turn off. The center of our galaxy is currently off. And so that's why I'm going to be extremely interested to see what the image looks like for the center of our galaxy compared to M87, which is a currently very active and very powerful supermassive black hole. You see what I mean?
Yeah, perfectly. Yes, a very, very clear explanation. Yeah, so why don't we go back to we'll put now the image of the M87 black hole, the Event Horizon Telescope image. Okay, so why don't you explain people who are looking at the event, explain a little bit the image, because it's not obvious for everybody what is the black, what is the bright stuff, etc.
No, you are seeing the light, which of course is the radio waves, is from material which obviously is very close to the event horizon, but not quite in it, obviously. And the dark shadow is the shadow cast by the event horizon. There's No light can come out of that. The light is in a ring because that's telling you about the way the disk of material, because as material falls onto a black hole, it doesn't just go straight in. It has some angular momentum, the famous story of a rotating skater that has angular momentum, and a material forms a disk around the black hole. The brighter part of the disk is actually the part of the disk coming towards us. And that's because the velocities of rotation are so enormous, they're a significant fraction of the speed of light, that you get relativistic boosting in the direction in which it is traveling. And you also have light being bent from the far side of the black hole, because it is being bent by enormous amounts.
Okay, Phil,
Right.
thank you very much. I don't know if there is any question.
No,
Elena?
not yet. But just Jacob asked if could the visual spectrum of GTC have contributed to this research in any way? I don't. This research I referring to the latest image of a black hole.
Okay, to the image of a black hole.
Maybe
in
not this one.
1987 is taken with a resolution which is thousands of times better of what the GTC can do. Yeah.
Or any optical
Or
telescope.
any
Yeah,
optical telescope.
because it's optical,
Even
yeah.
if you put it outside the atmosphere, because we have
Yep.
here an additional problem, which is our atmosphere. Even so, GTC is contributing a lot in the research of black holes in general by studying. Basically, if you're not able to image the black hole itself, you can study in much details the environment, which gives you indirect evidence of the central engine. And here they have been obtained very impressive results about, for instance, the kind of outflows that not only come from in form of jets, but also in form of massive winds from the accretion disk. Yeah, so matter before part of the matter does not fall into the black hole, in these binary black holes, but is ejected by the accretion disk. Yeah.
And Romano, the telescopes like Gran Telescopio and Hubble can contribute substantially to that, because you can see these outflows in the optical. You don't need the resolution there. What you are getting is spectral resolution, and that's telling you about the velocities of the material that's being ejected.
Right. So.
Okay.
Yeah, so just the last thing, as we mentioned before, this is the project that contributed to obtain this photo of the black hole. So GTC is not here, the map.
That's right.
We are here close to Africa, so Canary Islands, but we are not in the path of the blue path.
Yeah, of course.
But Spain, of course, did contribute to this through
right.
the telescope in the mainland.
Yeah.
Okay, Phil, I would like to thank you very much. Yeah, because your explanations are so clear. Yeah.
My pleasure.
And is really a honor to have you contributing to this attempt of GTC to get to people during the night of the GTC. From inside the GTC. Actually, here we didn't say people, but we are next to the control room.
Yes, we are.
GTC, so we are
right.
not far away. We are here up on the mountain. It's pretty.
Yeah, let's have a look at this is the camera, the external camera of GTC pointing to the dome, the telescope, and the crescent moon.
Yes. And,
sounds wonderful.
And
I've been there many times and wish I was with you now.
It's a good night. Looks a good night. There's a lot of moon, so tonight we will observe mainly in the infrared, but it's a pleasant night. So finally, even temperature is 10 degrees. So
it's quite warm.
It's warm to be at night up on the mountain. So Phil, thank you again.
Thank you, Phil.
My pleasure.
Perhaps we'll disturb you again in the future.
I'd be delighted.
Okay, bye-bye.
Bye, Phil. Thank you. Bye.
Okay, so just take a look outside, because we are looking. You can see the telescope is illuminated by the moon. Yeah.
Right.
Actually,
so
everything looks clear. Up on the zenith, there is the moon, so the camera responds. There's a lot of effects, because this is a fisheye camera with a dome on the top. So there are a lot of reflections and halo produced not only by the optics of the camera itself, but by the dome. But here we have the first images of the sky as seen from the camera we have mounted behind the secondary mirror. So this is you see how many stars you can see even with a standard 50mm telescope, and even with a very bright moon. So what the GTC is pointing somewhere there.
It's a kind of halo there. It's
this is another reflection of the moon. Now you see something moving. Actually, the telescope, of course, is moving. So now the telescope is moving and pointing to another direction. If you look from inside the dome, you see how bright is the moon.
Yeah. Sorry, Romano. Can I? Maybe your microphone is a little bit low. So can you put it here? I think it's better, because I think
perhaps it's a matter of batteries.
Could be, but maybe we can change the batteries later. Right. So our the people via the chat.
So the other thing is go to the control room, and actually what we can do, Elena, I think, is to call our guest who's anxious to participate. Dave is down in the control room. Actually, I leave you again to call him.
Okay, right.
To call him. I will be back in a couple of minutes.
Okay, right. So, thank you, Romano. Right, so we are going to call our guest, Dave. So let's call the control room. You can see the control room here. I am on another room next to the control room, but I'm going to call him. So let's see. Yes, our astronomer is wondering if he can pick up the phone.
Se ha equivocado.
Okay, that's Romano there in the control room. Hello.
Hello.
Hello, how are you, Daniel?
Fine, thanks.
Good. Okay, so I think we can introduce you later, because we have a video about you, a little interview we recorded a few days ago. But maybe can we speak with Dave? Dave, it's up here, I think. Hello, Dave.
Hello.
That's Dave.
No mic.
Yeah.
Romano has the mic.
Okay, yeah. So Dave has no mic right now, but maybe in the meantime we can speak with astronomer. Okay. So by the way, first let's introduce Dave. You can say hello with your mouth.
Hello.
But anybody can hear you. We can hear you in a while when you have the microphone. So now we can speak with you, Daniel. Daniel is our astronomer. Okay, so very, very glad to speak with you tonight, because you are going to tell us more, if you want, about the currently observations. Right. So what are they doing right now?
We just finished to stacking the primary mirror, and now we are moving to the platform Nasmith A.
Okay.
To observe the galaxy M51.
M51. Okay. I think I have a picture I'd like to show you a picture of this galaxy here. Yes, that's Messier 51.
Maybe I can transfer the call to the other.
But we can look, we can use the other camera. So, hello. Now I can see you closer.
Okay.
So maybe we can see, we can zoom into the computer and we can
Yes.
have a closer look at the,
Okay.
okay.
We can point right now. Yeah.
Yes, so.
Let me give you then.
Okay, so just a
This
second.
is the procedure we use to operate telescope.
Right?
I made a query to the database of the object that the researchers have saved in our system,
Right?
and I provide to the operator, Alvaro, with the parameters to point the telescope, and then we're gonna see this galaxy with our telescope.
Okay, good. Right, so this is the galaxy, the so-called Whirlpool galaxy, is Messier 51.
Yeah, this object is interesting right now. It's under study because it's showing a nova.
All right.
And it's very curious because it's not similar to the previous known object of this type.
Right. Actually, we will talk later about this eruption. So eruption of this star, and actually, yes, I think we can talk later. How about GTC follow with this explosion, right?
Okay.
Good. But if you want to explain maybe more in detail what we are looking at right now.
Okay, about the process. Yeah. This is the control panel for the instrument we're gonna use, which is EMIR. EMIR is an infrared instrument.
Good.
Near infrared instrument, and we are going to take broadband images. This is the field of view of the instrument. And here we have the filters to filtering the light that is coming from the source.
Okay.
And with this screen, I have a series of orders to set up those filters and the exposure time we have to use for this target. Everything that is in this XML is requested by the researcher that have studied how to optimize our time.
Okay. Yes. Good. And what about the weather parameters right now? Because we saw that we have a very good values, I think. So.
I don't know if you can see the screen with the parameter. Yeah. Right now we have not measures about the scene. But according to our measurements, it's about 0.8 arc seconds. So we have a more or less stable. ¿Ya estamos? Vale.
Okay.
Sin guiar, ¿vale? Perdona.
Oh, sorry. Yeah. Well, of course, you're working at. We cannot interrupt the operation. We understand. Of course, we understand that. Yes, we can see it now. We can see it on the screen.
Yeah.
Good. So as we were mentioning before, we have very good conditions tonight. Yes, this is a very important screen we have to look at anytime.
Yeah. We have to control that the observations we are executing are according to the weather conditions that are requested. Not every observation can be done under any circumstances or
Of course.
transparency. And well, this moment is optimum for the observation.
Yes, right. Okay, so maybe we can discuss later, or maybe we can talk with you later if
Okay.
you want. Yeah, so now I don't know if now we are a little bit busy.
Yeah.
with, yeah, so don't worry, we perfectly understand that's your job, so we can call you later if you want.
Yes, thank you.
Okay, thank you, Daniel. Thank you, thank you.
Thank you.
Okay, right. So, okay, I think we can maybe speak with Dave.
Still don't have a mic.
Or, yeah, okay. So, okay, so Dave, you will use my microphone. That's it. And you can come here a little bit closer.
Okay, hello. Can everybody hear me?
Yeah.
Pues,
I can stay on this side, no?
Yeah.
eso no hace falta, ¿no? Ahí va. I'm back. Hi,
Hello.
Dave. Let's put the big panel. Dave, which one was it? Here. Where is it? This one. Here we are. Yeah. So I know this gentleman since 2008.
2008, yes.
And actually, well, he's younger than I am, but we made followed more or less a similar path because he had been a student where I was working, and then I was a student where he was working when he had a fellow in Chile. So I mean, the world of astronomy, especially is experimental astronomy, is not that big.
No.
But also, I must say, I mean, as I enjoy very much. It was. I'm very happy that Dave, after studying in Manchester,
Yes, that's right.
and then being a student in La Palma, yeah, and then he was a fellow in Chile at the European Southern Observatory.
Exactly.
Yeah, and then he came back finally. Well, finally
Came
not
home,
finally.
yeah.
He
Came home
back
to the Canary Islands.
To the Canary Islands. So we are collaborating together, and this is the title. Actually, we've been talking about black holes. Yeah, but we're gonna.
Now we have to talk about things that you can really see
Yes,
directly.
something bright. Yeah, stars and nebulae. And so this is what prepared by our friend Jacob. Yeah, and let me put the pointer. I would like to say we don't say anything, but just point at this cube. So I would like to know if anybody of you has any idea what it is. Yeah. So we will leave some time because of the delay for people to answer. Jacob, you're not allowed to say anything, yeah. But then we will come back. So now what we want to talk about is a bit about life of stars, and especially when they die, isn't it?
Yes.
Yeah. And especially how we observe them with the big telescope like the GTC, no, because you have been using the GTC
Exactly.
for as well as other very big telescopes in order to study the final fate of stars.
Indeed.
Yeah. Can you want to put an image just to
yeah.
start straight? Remember, you have to tell us. This is the first contest of the day. You don't gain anything, but this is the first contest.
Just respect.
Yes. What is this? What is this? Okay, so let's go to our nebulae because Dave and I work with a fantastic nebulae, and take one that Dave, you choose one that you have been working on.
Why not this one?
Okay.
It's
beautiful. You tell people what it is.
So this is a planetary nebula, which the name is a very bad name because it has nothing to do with planets. The name planetary nebula comes from the guy who discovered the first planetary nebula, William Herschel, a German-British astronomer, who also discovered the planet Uranus. And he thought that the first planetary nebula that he saw looked a little bit like the planet Uranus. And so why did it look a little bit like Uranus? So he was used to cataloguing stars, which looked like points through his telescope, but these things were sort of diffuse, milky balls, the same as a planet looks through a telescope in those days. When in fact, planetary nebulae are the final stages of stars like our own sun. So when our own sun runs out of fuel, it throws off its outer layers and exposes its very hot core, which then ionizes the material which it's thrown off and produces these very beautiful nebulae. And one of the things that Romano and I are most interested in is if you have a spherical star, which almost all stars are spherical, when it throws off its outer layers, it should be roughly spherical as well. So how can you go from a spherical star to something that's so aspherical like this, which is like an hourglass kind of shape? And Romano has his toy.
Yeah, this is not an
Nebula.
easy question, as that was the topic of my thesis many
And the
years
topic
ago.
and the topic of my thesis.
Or your thesis. So it's a debate that is lasting for 30, at least 30 years, probably,
Yes.
probably more, because since the first drawings of a planetary nebula, people noticed that the spherical structure of a star is completely lost in many cases, actually the majority of cases. So when I was a student, that comes back to the time I was in Chile as a student, that was in the market of Santiago de Chile. Yeah, there were people producing these kind of things. I asked them to, actually individual ones, no? I asked them to put two together, because I wanted to understand how, actually this is the same nebula we see there. I don't know, you see it here. So I wanted to understand how you look at them depending on from where you look at them. So, because that time we were taking probably the first good images of planetary, not good images, first high quality images, because there were new telescopes and there were new detectors. So actually there was the space telescope also was launched in those days. So there was a big revolution in understanding the morphology of planetary nebula. So what? After 30 years.
So after 30 years. So after 30 years we know what it isn't, I think. So people thought that maybe it was rotation. So if you make a star spin really fast, then maybe it would throw more material off in the plane in which it spins. And it turns out that if you want something to spin that fast, it never gets that far. It never gets to this stage. And the other option that people thought of was magnetic fields, which in astronomy is the get out. If you don't understand what something is, you blame it on magnetic fields and you move on and look at something else. But people have persisted and looked for magnetic fields in the heart of these things and have discovered that there are none. And it turns out that if you were to have a magnetic field strong enough to make these kind of shapes, it wouldn't last long enough, it would be drained. So we're really left now with only one idea, which is that instead of being one star at the center of these things, it's actually two stars. And the stars interact when the main star gets to the end of its life, and that is what causes these shapes. So in the wastes of all of these bipolar nebulae, there is a pair of stars orbiting around each other, very close together. And in fact, in this, the object behind us, there is a pair of stars that has been proven.
So shall we invite our friend Harry to join us? So we continue the discussion, because there are, of course, a lot of things to understand, and a lot of work that we are doing in order to understand really which is what happens in the center there, because it's very difficult, isn't it, to see the two stars.
Absolutely. So maybe we can talk with Henri about how difficult that is.
Yeah. Okay. So let's see how we do that. We
should say hello to Hector as well.
Hello, Hector. Hector Montero, another good friend. Hangout. So let's see, Harry, if you can hear us. Can you try to connect with the link that we sent you?
I think we need to connect ourselves, no? Because this is not. Or we can send him an invitation.
Yeah. Just invite Harry.
Sound is gone. Good now.
Yes. So we are learning little by little about all these kind of sliders and buttons to run all these different assets at the same time. So while we wait
Hello,
for...
Gianluca.
Gianluca's there. Wow. Ciao, Gianluca. One day we will do one streaming event in Italian. Yeah, here.
Not with me. Not with me.
Not with you. So let's start thinking about. First of all, because of this, okay, you have to understand which is the three-dimensional structure of an object. Because in astronomy, what we have. Oh, Harry is there.
Hello, Romano. Hello, Dave.
Good night,
Hello.
Harry. How are you?
Hi, thank you.
I think we need.
I enjoy very much the whole show until now, so I hope it's not going to decline.
Okay, we are centering now in the screen, so at a certain point you will appear. There you are. There you are, so everybody can see you. So where are you?
I am in Munich, which is the ESO headquarters. You mentioned ESO, that you both went there as a student and as a fellow, but in Chile. But we have also the headquarters, which are in Munich.
So yeah, tell us a little bit more about you, about your career, just to understand.
Well, I had a typical career of an astronomer. I guess I in Brussels, Belgium. Then after that, I decided that in fact maybe I should do something else in astronomy. So I went to journalism, and I worked as a journalist for a while. But then I went back to research, and I did a postdoc. So studies after the PhD. I went to Japan first, and then I went to the UK. In fact, to Wales. So. And after that, I went back to Belgium, and then finally I moved to ESO here in Munich.
Okay, so we started with Dave showing pictures of planetary nebulae. Some of them you have been contributed a lot. In fact, Dave has put the picture of FG1. So we were starting trying to explain which are the steps we do in order to understand these kind of objects. And we started talking about the limitation of observations, because nebulae are three-dimensional, but we only see things which are projected on the plane of the sky. So we have a very limited information about their true shape. And also we can measure movements, but really we are limited in measuring the movements, the expansion of the movements of the particle of gas in the nebula. We are also limited about that, isn't it?
Yes, of course. This is the usual problem in astronomy, where we can basically only observe with light. But we can take images, but we can also take spectra, of course. And with the spectrum, we can measure velocities. And so we can also then measure how the material is moving inside the nebula. And this is also very useful to understand the three-dimensional picture. But what we can also do is to try to find if there is anything inside this planetary nebula. And this is what we have been spending most of the effort, because we think that, as Dave explained, that most likely the reason why they have this kind of shape is because there is not one star inside the nebula, but there are two stars. And there are two stars which are forming a couple, and they are waltzing together. And the question is, of course, how are we going to show that there is indeed two stars in those planetary nebula? So we can do that by two different ways. One is to simply measure the light of the central star and measure it as a function of time and see if it varies in a very specific way. And if it varies in a specific way, most likely it means that there are two stars, in fact, and one is very hot and is illuminating only one side of the star and not the other side. So when the two stars are turning around each other, we see a change in the light from the central star.
So in fact, Henri, we can, before you move on to the second, we can show an example of that. It's from
Great.
from a paper that we published together earlier this year. So this is the planetary nebula called M31, which is kind of similar to the one that we've just shown. And if I can point, no, it's too far away. Point.
You can use the pointer.
Use the
if you like.
pointer. That's better. Yeah. Okay.
Just go at the top of it, and you can make it.
So the central star is this blob here. And you can see that the problem is that the two stars are so close together that from the Earth, we can't see both stars. They look like one star altogether. So we do exactly what Henri was saying, and we take images one after another of the star and measure how its brightness changes. And in this case, we studied this with a telescope in Chile and followed it over a few nights and saw that its brightness changes, and it changes like this. So on the right-hand side, you can see how the brightness changes over a period of about 3 hours. And on the left-hand side, you have a little toy model of what the stars look like. So the sort of big yellow star is a white dwarf, so that's the dead or dying star, which has thrown off all of the material. And this red star is the companion. So this is a main sequence star, like the Sun, but much lower mass, maybe less than half the mass of the Sun. And just as Henri was saying, you can tell there's a change in the temperature of the side of the low mass star, which is pointing towards the white dwarf, because the white dwarf is very hot, maybe 100 times the temperature of the Sun. And so it heats one face of its companion. And then depending on how much of that hot spot we see, the light curve or the brightness from the system changes. So here in this system, we have two different things happening. So we have eclipses, where one star blocks the light of the other star, which are these dips here and here. And then also this sort of peak is because we are seeing more of the hot spot of the second star. So this is one of the ways that we can find these binary systems.
Okay, just for people to understand, really, this is a white dwarf, so it's very small.
It's very small.
Yeah. Just to hear, how big is the nebula?
So a few parsecs, which is in light years.
Several solar systems.
Several solar systems, yes.
No, something like that.
Yes.
Between and the closest star to us, in fact. This is the size of the nebula, while the distance between the two stars, it's basically only a few times the size of the Sun. So they are really very, very small compared to the size of the nebula.
In fact, in this case, which is a very special case, which is one of the reasons why I show it here, the distance between the two stars, between here and here, is less than the distance between the Earth and the Moon. So they are really close together.
So we now entering, okay, we're studying these binary stars because we want to understand why planetary nebulae achieve these fantastic shapes. But the phenomenon of stars living in binary systems, in pairs, in couple, is a very common phenomenon in the universe, isn't it?
Yes, most of the stars are in fact in couples, so they are in a binary systems. So that's why, in a sense, the Sun is more the exception than the rule, because for stars which looks like the Sun, it is about 60-40%. So 60% of the stars, like the Sun, are living in couple, and only 40% of them are single. But I guess it's because the Sun is single that we are here, because it's much more easy to make a planet which is stable around a single star than something around, of course, two stars going around. But there are binaries everywhere, and in most cases, most of the very interesting things that happen in the sky is because you have an interaction between two stars in a binary system. So this is also how you can measure the masses of things that you cannot see. This was the example from field charts, of course, before, where they could observe a black hole without seeing it, but simply because they could see that there was a star moving around something, so there must be a black hole. And there it's again a binary system. And also the astronomer at the GTC said he was going to observe a nova. A nova is, of course, the result, again, of the interaction of mass transfer inside a binary system. So one star is, in fact, feeding onto the other star.
Actually, as you're speaking of novae, yeah, we are putting an image of GK Per, which is the name of a nova that exploded in 1901. Okay, and this is what we have 100 years later. So this is the matter that has been ejected during the explosion of the nova. Actually, we have a movie. We have patiently, well, it's a real movie, this one. We have patiently taken images year after year, especially in the last 2 decades. You can really see that the nebula is expanding. In this case, it's expanding at a considerable velocity, 1,000 kilometers per second. So here we are always speaking of astronomical number. Everything is very big. If you come back, the measured expansion now is expanding. You come back, it goes back exactly to 1901. Actually, there are different kind of explosions of stars and different kind of interactions. So as we are speaking about nova, perhaps here is convenient to say that this is the kind of explosion in nova are thermonuclear reactions, yeah, on the surface of white dwarf, which are caused by accumulation of matter from a nearby companion.
So it's a little bit like the opposite of what we've been talking about with planetary nebula, where in a planetary nebula, the companion star, the second star, helps the white dwarf to throw off its outer layers, helps the star to go towards a white dwarf and get rid of all of the outer layers. Whereas in this case, the white dwarf is stripping material from its companion. They are so close together that it's tearing material off, just like Phil talked about with the black hole at the center of our galaxy. There will be a star that will pass close enough to tear it apart and start to eat some of the material. So in a nova, it's basically like that. The white dwarf is eating the material from the companion, and eventually it reaches a limit above which it can explode. It undergoes a thermonuclear explosion.
So, does it mean that the star disappears?
No, the white dwarf stays there. All it does is it blows off the outer layers, and in fact, these novas can be recurrent, so if everything stays the same, it just switches off for a little bit, exactly like the black holes in our galaxy, and then after a little while, the star again begins to take material from its companion and will erupt again, and they're called recurrent novae. And in fact, one of the very interesting puzzles of recurrent novae is, with each eruption, does the white dwarf grow in size or does it reduce in size? So does it always throw off all of the material that it's stripped from its companion, or can it increase? Because if it can keep increasing, it might eventually reach another limit, which can make a supernova, which is called the Chandrasekhar limit.
Okay, so these are an example of interaction between a very small and compact star and a normal star, usually low mass. Now I put in the screen another image, Araquari. You will see it in a few seconds, but I would like ask you to comment about this kind of stars, which are called symbiotic or symbiotic stars.
Yes, indeed. So symbiotic stars are a little bit the big cousins of the nova ones. There, in fact, what you have is that you have a star which is a giant, which has a companion which is also typically a white dwarf. And the giant is losing matter also, but mostly simply by wind, because all the stars are losing mass, and they are losing mass by wind most of the time. And again, some of this material is going to be accreted by the white dwarf. So it will fall onto the white dwarf, and then it can produce again some kind of strange phenomena. But most likely what happens is, because there is a companion, the material that is going off from the giant does not go into a spherical way, but is in fact being completely disturbed, and that's why it gets this very funny shape that you can see there on the screen.
So here we have a slightly different family of binary stars. So now in this case we have again a very compact and old star, but in this case we have a huge star, a red giant.
Yep.
Yeah.
So a star that's exhausted all of the hydrogen in its core, which is the main thing that the sun burns. And when a star exhausts all of the hydrogen in its core, it starts to burn hydrogen or helium in strips outside of the core, like an onion in shells. And when that happens, the star inflates to maybe 100 times its normal size.
And this is something that will happen to the sun in how many years?
A few billion? No?
5.
5 million, or 6 million years. Yeah, billion years, sorry. So these are symbiotic stars, a very interesting object. Actually, if you see here, this is not a static image, but this is, you see the expansion of the nebula, over a period of 20 years. And these things we are showing is also to show that really the universe changes. If you are patient enough, or if you have telescopes good enough, you can really see not only what is projected on the sky, but how it changes over time. Yeah. And now we'll put another one, which is one of my favorite nebulae. It's called, which is the name? But it's a butterfly nebula, or
yes, no, it's the butterfly.
Double black butterfly, something like that nebula. And this is again is a real video. Ari, you know this object as well, M29, isn't it?
It's not my preferred one.
So what you see here, something extraordinary, I think. So you have this funny shape. Actually, why don't we are down this funny shape, which is, yes, 2 lobes, one on this side. I'm not painting very well, sorry. On the other side, so it's something again that something that forces the star or the stars, as we think, to lose mass in certain directions. So, and this is probably again due to the fact there are 2 stars there instead of one or only one star. But what you can see here is that a sort of lighthouse. The green stuff is rotating. You have to think these 2 lobes, yeah, here like this one, 2 lobes. Let's put it in big, if I can do it. Yeah, there it is. Let's go. So I can use, so this is very similar to what we have here. Yeah, 2 lobes, so the material is flowing this way, is flowing that way, but in addition there is something that is rotating from one side to the other side. So it's like a lighthouse that is rotating, and they're rotating at the same time on both sides. So it really is a very peculiar effect, and again, it rotates in about 90 years. Yeah? And we think this is related, in fact, to the orbital motion of 2 stars which have a period orbiting around each other in 90 years. The problem is that we have not been able to find any evidence that there are 2 stars instead of 1 star. They are very still, for this kind of object, this one, the butterfly nebula, very weak evidence of there are 2 stars in the middle. But I'm sure that all of us, at least all of 3 of us, would bet
believe us.
This is a binary star.
An important thing to mention is that the longer the periods of these things, the more difficult they are to find. Because the longer the period, the further apart they are. And so the smaller the variations are when you take images one after another. And also the smaller the variations in the radial velocities. Not to mention that you have to keep observing the stars for 90 years to be able to see the full.
There was a question, Dave, by Isabel.
Yeah. About how does it help, or
No, related to the previous one. How does the
white dwarf star absorb what it is? How does the white? Okay, so the white dwarf, if we're talking about the novae, so the white dwarf is degenerate, which basically means that it's so only held together. So gravity is crushing it down, and it's only held together by the force that stops electrons from being put into the same place. And so all of the material that falls on top of that basically goes into a shell around the outside of it. It doesn't get included in and mixed in. It gets kept on the outside.
Actually, if the accretion on to the white dwarf is low enough, you have time to process the material. What does it mean to process? To have thermonuclear reactions or fusion. Yeah, so you can process the material, you don't explode.
On a slower time scale.
But generally, the flow of material onto the white dwarf is too fast. So material accumulate until it reaches a critical mass, and then it provokes a thermonuclear explosion, which is we call it a runaway. Okay, but in principle, if you tune the transfer of matter from one star onto the white dwarf to a level which is low enough, okay, then you, well, actually is a bit of the opposite. If it's too low, you provoke another explosion. If it's a bit higher, you can process it. It is a very critical equilibrium. It's very difficult that you can tune in order to process the material. If you accrete too much, then you don't even have time to make an explosion. You just create an extended atmosphere, so the star becomes like a red giant.
So the next question is: so there's no eating. So there is
eating. Yeah.
Because in the time while it keeps taking the material, it increases in mass until the explosion occurs, and then it throws away some of the mass.
Yeah, exactly.
But we don't know whether it throws away more than it eats or less.
That's the point. But in principle, you should be able to retain some of the mass that's been accreted, yeah, in order to little by little to grow. Yeah, but this is the way we think some of the explosions like those of supernova occur. Yeah.
Mm-hmm.
So another question, Miriam Garcia, is there a catalog to see observationally how the PN evolved from proto-PN to amazing forms, plotting with the PN age? Wow, it's a difficult question.
This is a difficult question, because in fact there is so we don't actually have any images of protoplanetary nebulae, but a lot of protoplanetary nebulae are very complicated and have, rather than being sort of simple structures like this, if you could call it simple, which have two lobes, so it kind of goes in that direction, they have multiple lobes and they look almost like starfish. And really we don't understand very well how they form, nor do we understand how do you go from a starfish to something like this in an evolved nebula.
Yes, it's a different.
It's a very open question.
Yes.
We should go back to.
Okay, let's. As Harry is still here, let's speak about some other. First of all, to show this fantastic nebula. So the kind of shapes of planetary nebulae are amazing, and this is a strange nebula because in the middle there is a star which is not hot enough, to have produced to say illuminate. It's not illuminate, to energize, to power the gas in the nebula. So again, we think there must be a
So there have been several other cases where people have seen stars at the center of nebulae that shouldn't be there, that don't fit with being at the center of a planetary nebulae, and in most cases we've been able to show that they do have a binary companion, where the other star is the missing white dwarf.
But this is a difficult guy, yeah? Isn't it?
And so far this one has eluded us.
Is a difficult one. And then there is some...
You can do that also by combining, of course, observation in the visual or the optical, like you do with the GTC, with observation in the UV. So if you go to the ultraviolet band, like using, for example, HST telescope, there you could detect, in fact, the hot white dwarf in the UV that you cannot see in the visible. So this is one way to indeed make sure that there are two stars inside.
Exactly.
The other way that you can do it is also to see that the star that you see inside this nebula, which indeed is not hot enough to be able to have ionized all the material around it and create this beautiful nebula, but you can see that this object is in fact enriched in carbon or enriched in what we call S-process elements. And those elements, they are only produced at the end of the life of a sun-like star. just before they become a white dwarf. So the fact that you see a star which has been enriched in these elements means that it must have received this material from the companion, which has now become the white dwarf, and we don't see it anymore in the visible, while this one is still visible and is enriched in this material.
So yes, the S-stars are the factories of elements. Yeah. When you put binary stars, you complicate even more the scenario. And
You make it interesting.
yeah, in fact, you can, in some cases, more easily do certain things than if you have a single star, isn't it?
Indeed.
Okay.
Exactly. I mean, most of the things that happen which are interesting in the sky is because there is binary interaction. Single stars are so boring. You know?
Our sun is not that boring. I mean, so Henri, here we just to give a general picture. We have been speaking about binary stars, and the kind of examples we've been giving are those which are very close to each other. So they orbit around each other in hours or days. Okay. Then we have been speaking about symbiotic stars. Their orbital periods are of tens of years, hundreds of years, or even several hundred of years. And still, even so, which are very separated, they are still interact in order to make this nice phenomena that we have been talking about. So what happens if we go to the other end? Which are the shortest period binaries that we have in the universe?
Well, I'm not sure anymore what is the record, but I think the record is in fact two stars that are going around each other in 5 minutes.
So you can imagine that, yeah? This is
so those are two white dwarfs, in fact, going around each other in 5 minutes. So by the time that you have finished your show here, they will have already gone, 30, 40 times around each other.
So they must be very small, very compact, yes, and yeah.
Those are white dwarfs, in fact, which are going around each other. Yeah.
Here, recently with Gran Tecan, we have been observed one object of this kind, which has an orbital period of 10 minutes, and is very spectacular to see with Hypercam, which is a fast camera here. So it was really, we were able to take an image also because GTC is big, so we have a lot of photons every few seconds. So it's very spectacular to see how the luminosity changes in real time. You can see growing on the screen while you're sitting looking at it. It's spectacular.
We should mention as well that these very short period systems are also very interesting, because the period might be 5 minutes now, but it won't be 5 minutes in 10 years or in 15 years. Because these stars, when they orbit around each other, they're so close that they actually lose energy through the emission of gravitational waves. And so the radiation of gravitational waves actually takes energy away from the orbit and brings the stars slowly closer and closer together. And this is another way that we think supernovae might occur, supernovae type 1a, where you have two white dwarfs that are particularly massive. That's the video.
Let's put the video.
Two white dwarfs that are particularly massive, that slowly, via the radiation of these gravitational waves, get closer and closer together until they merge.
So this is what we are seeing there in the video.
Yes, so this, in fact, is a very strong candidate system for one of these mergers that leads to a type 1a supernovae, which we discovered using Gran Tecan a few years ago inside a planetary nebula. So there you have two white dwarfs where we think the total mass is something like 1.6 times the mass of the Sun, which is above the limit, this magical limit called the Chandrasekhar limit for a supernova type 1a explosion.
Okay. As we are speaking about binary stars and close binaries, why don't we take one of the results of the week of Gran Tecan, which is this one. Okay, so do you want to comment a little bit about this result? This is the study of a binary star, yeah?
Yeah, so it's a binary star very similar to the stars that we've been talking about. So it's a white dwarf, so the little guy here is a white dwarf, and then this star...
Put the pointer.
There you go. Pointer, yeah, sorry, I'm not pointing. So this little guy here is a white dwarf, so that's a hot star, something like 2 times or 3 times the temperature of the sun. And then this is a subdwarf star. So a subdwarf is a very small star, but basically the same as the sun. So it's about 15% the mass of the sun. And it's also, Henri talked a little bit about the chemistry of these stars. So this star, its chemistry says that it's a very, very old star because it has almost no enrichment in materials, which means it's probably one of the first generations of stars. And these are particularly interesting because they can tell us a lot about stellar evolution and about the physics of these systems. And when you have these stars in binaries, it gives you a means to measure their parameters very, very accurately.
So this is, again, this is what comes out in the newspapers when we make a discovery. This is some explanation and this beautiful picture. Mm-hmm. Okay, this beautiful picture is not real.
No.
Yeah.
No.
Okay, we have to be honest. Yeah, always. And but it's not obvious. I mean, it's obvious for you and for me, but not for everybody. So this is just what we call an artist's impression. So a sort of a representation of it. I think is as we are here observing these kind of things with the GTC tonight, it's interesting to see which are the data, what we really do here. And instead of taking that picture, we do something like that. We make a graph.
Yep.
Yeah.
So this is taken with the Hypercam instrument that Romano mentioned, which is a fantastic instrument, which allows you to take images simultaneously in 5 different bands. So when we take images with the telescope, it's not a color image like you would with a camera. It's almost always black and white, but through a filter. So here they use 5 different filters, going from almost the ultraviolet through to the infrared. So U is for ultraviolet, G is for green, R is for red, I is for infrared, and Z is past infrared, although still. And so you can see these little points here, which are so small and so close together that you can't see that they are separate points, are actually each of the individual observations, and this is the brightness in each of those.
What's there is time.
Yes, so time. This is time, but it's split into orbital phase, so 1 unit here is 1 orbit of the binary star. And so each of these little dots is 1 measurement of the brightness of the system in each of these colors. And so using those, you can measure extremely precisely how long each of these eclipses are. So these dips are when the subdwarf passes in front of the white dwarf. And even in the infrared, you can see this very slight dip. That is when the white dwarf passes in front of the much fainter, even though it's much bigger physically, much fainter red dwarf. And so you can see that they have a model fit here where the top black line is if they ignore the eclipse, and the bottom black line is if they take into account the eclipse in the model. And so using this, they can measure extremely precisely, to better than 1%, the mass and radius of this very low mass star, and show that it fits perfectly with the current models that people use for these stars.
So you mentioned we can measure the radius of a star. So Henri, as you are an expert, so even with very big telescopes, in principle, it's very difficult to measure the size of stars because they are very far away, isn't it? So why don't you tell us a little bit, how do we measure radii, in which cases we can really resolve the size of a star?
Yeah, so there are several techniques. I mean, one of them is the one that Dave just explained, which is using photometry. When you are lucky in a binary system that you have some eclipses, then you can have an idea about the size of the star. But you can have some other means is by using interferometric methods. So when you do interferometry, what you are doing now is not using only one telescope, but you are using several telescopes together, and you combine the lights of those various telescopes together. And by doing that, in fact, you are able to see details that corresponds no more to the size of the mirror. At the beginning of the show, you explained why it is important for the GTC to be big with 10 meters. But if you want to see big details, you want, in fact, to have several telescopes, and what matters is the separation between those telescopes. So we can use interferometry, for example, at ISO in Chile, with the small telescopes, we can combine the light of several telescopes, and the separation between the telescope will then be up to about 200 meters, which means that we don't get the light that would correspond to a mirror of 200 meters in diameter, but we have the resolution of a telescope which is 200 meters in diameter. And this allows us then to have a resolution which is basically 100 times better, or maybe 10 to 50 times better, let's say, than the biggest of the telescopes. And by using this technique, we can indeed measure, and we have done that, for example, the radius of stars like red giants in symbiotic systems, the one that you mentioned before, and we were able indeed to measure precisely their diameter.
Okay, fantastic. This is one result of the week. Previous week we had another one we'll talk about later. And before say goodbye to Ari, we move to another phenomenon we have not yet spoken about. Is what happens. We have talked about mass transfer from one star to another one if it's close enough, yeah, but not what happens when they merge. Or what can happen and how often that can happen. We're talking about that because we will see then later an observation that the GTC is taking of one of this, what we think, this kind of phenomena where the two stars really merge. Yeah, they don't explode, they are not destroyed in the process. Yeah, and we can observe them in the process of merging. So merging of two stars is an important phenomenon in astrophysics, or something that happens very rarely.
Well, I think we don't know the answer to this question. This is one of the important things that indeed, to explain, for example, the planetary nebula that we have seen before, we know that, we think that one of the way to produce these envelopes is to have indeed a binary inside and to have those two stars, which were initially with a very long periods of, like you mentioned, several years or tens of years. But then because one of the stars became so big that the companion entered the envelope of the star, and then by tidal drag simply came closer and closer and closer to the core, and finally the orbit shrunk and became of less than 1 day. But the thing is that for some reason, in some case, this evolution is indeed stopped, and we then have a system with a planetary nebula, and inside we have only one. We have two stars with very close. We have a few candidates for that. This, in fact, spiraling does not stop at all, and the two stars will simply merge, and they will form only one more massive star. And when this happens, what happens is also what we call a red nova, in fact. So it's another kind of nova, where you will also have, for a very small moment in time relative to the life of the star, the star will become much more luminous, and will also eject a lot of material. But then after that, the star will become simply bigger and more massive star.
Okay, so I mean, merging is probably an important phenomenon. Yeah, and so a few years ago, the evidence was not much, but now there is a lot of effort, yeah, in order to discover this phenomenon. What you mentioned, a red nova, that we think are novae that are more luminous than normal novae. Yeah, and also instead of getting bluer with evolution, they become redder. So at the very beginning, it was a big mystery. But since the very beginning, the most likely explanation is that was produced by the merger of different stars. So until a few years ago, we had only evidence of a few of them, or very few actually, 2 or 3. And nowadays,
before 2000, it was maybe 2.
And now there are not many more, but there are more.
There are more.
There are more. And now we have one that has been observed by the GTC yesterday night and the night before, and also something that we saw an explosion in a nearby galaxy. Well, it's not really nearby. It's 50 million light years, but it's there, M51. So, Ari, I don't know. What do we do? Do you want to see the images of M51 and comment
Yes, of course.
with us? Fantastic. So we move. You are online, but we are showing. And this is the galaxy. Okay, this is an image taken. Let me see in the red band. Yeah, and let me make it bigger. I don't see it. Dave, you know better than I. So
Yes.
please.
So the star which appeared, so that's what a nova is, it's a star that wasn't there before, but is now there, is this guy there. And you see that?
Make it bigger if you like. Or, yeah. Actually, this is an image taken, is a we call a red nova, so must be red, isn't it? So why don't we go to the red? This is already the red, but why don't we go more to the infrared? So here, the Gran Telescopio has taken 6 images of this galaxy in the last few days, and we show all of them. The 3 of them are in the visible band. So one is in the green, say green color, green bluish. One is red, and one is redder than red, we call I band. And then has taken 3 images in the near infrared in 3 different wavelengths that we astronomers call H, J, and K. Okay, so if we go to a very, let me look for it. We see all of them. We take this one, and then we show a single one. This is the image of the same galaxy in the infrared. You see, the galaxy looks different. Yeah? Why? The galaxy looks different because depending on the wavelength you look at, you see different kind of emitters, the kind of objects that emit the light. So if you observe, for instance, in the wavelength we have been showing the image before, there was a lot of emission from hot stars and from gas, and from the gas. Okay, if you go to the infrared, light is dominated by cool stars, so which are much more frequent than massive stars, than blue stars, and also so the image of the galaxy looks more diffuse. So all the image you see here is basically dominated by red stars, which are very numerous. Some of them are giants, and most of the others are just normal stars. So if you go to infrared, we see the star that exploded is this one, isn't it? This
Exactly.
one.
Yep.
Okay. You see clearly, and it's quite remarkable, no? Because this is 50 million light years away from us, and still you can see an individual star so clearly. Yeah. Actually, if you give me this piece of paper, I don't know if there are some amateur astronomers looking at this event, because something we would like to do is to distribute to everybody those images. Yes, there are 6 images, and then ask you to make nice color images. So we'll open a kind of contest. Yeah, we'll think about the prize in the future. Certainly the standard, where is it? Certainly the standard GTC T-shirt. Yeah, let me take one. But perhaps we will think of something more. Here is the T-shirt, GTC T-shirt. So we are opening a contest who's making out of these 6 images the best color images. We will put in our YouTube channel. Then Elena will tell you tomorrow or in the next days. We will put the links where to download the images. But now let's go back to science. And by the way, if there are some amateur astronomer here, the exposure time, we have a 10-meter telescope. Yeah. And this is a relatively bright galaxy, so it's the catalog of Messier, so it's relatively bright. So the exposure time were of the order of, in the visible light, a few seconds, 5, 3, and 3 seconds, while in the infrared, where it's more difficult to observe, the exposure time were of the order in between 1 and
A few minutes.
and 4 or 5 minutes. So we really, clearly, this kind of objects for the GTC are bright stuff.
Should we try and show the video of the...
Okay. Let's see if it works.
So,
a bit too fast.
so it's going way too fast. So this is a GIF.
Move to
You do it.
Okay. I don't know if you can see it. Let's see. It's going too fast. There is something which is blinking, but very, 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 very fast. I don't know if you can see it. It's an image taken before and after the explosion of this star that happened beginning of January, isn't it?
Yes, at the end of January.
End of January. So this is a star, very bright, yeah, now because it's exploding. It's not really destroying the star itself, but it's expanding, is producing probably an ejecta that is very, very bright, and we can see it as far as 50 million light years. Yeah. So Dave is studying this star, yeah. And what is the idea? What is to really understand if?
So the idea is to try and understand. Let me turn this off so it's not blinking so much. So this is a color image that was made by one of our team of astronomers. Before I talk about what we're trying to do, so one of the things that we're doing is we're studying this with GranTecan spectroscopically because it's faint enough that we need to get the spectra with a telescope this big. But in fact, we can observe it photometrically, so take images of the thing even with very small telescopes. So this is an image taken with a telescope in Vienna, in Austria, by colleagues of ours there, showing how red the object is. So if I can just hang my pointer over the top, you can see that this red dot just underneath the cursor there, that is the red nova. Anyway, so the idea is to try and understand exactly what's happened in this situation. So we don't know exactly what the two stars were before. Were they massive stars? Were they low mass stars? We don't know exactly what is happening now. And we basically want to understand why do these stars merge while the other stars that we see at the inside of planetary nebulae, why do they survive? What is the difference?
Okay. So I think we can thank you, really. Thank you, Henri, for having contributed. It's 1 hour later in Germany, but we are astronomers, so we're used to stay awake. So thank you very much.
Thank you for organizing this.
Well, we'll continue. It's an experiment. This is a sort of pilot project to see where we can get with this kind of live streaming events from the telescope. And if it works, we will certainly do more, and we'll count on you in the future as well, isn't it?
Yeah, of course, please.
Okay. Okay, thank you very much. Have a good night.
Yeah, have a good night too. Ciao.
Good night.
Okay, bye. So I repeat, I put here, let's go back to our view, to our standard view. Here we show the 5 images that we have. So these are images. Here they are. Okay. So these are images of, let's see what happens if I do like that. It doesn't work. Yeah, so let's put it back again. Images of the same galaxy taken in different filters with different colors. Yep. This is the bluest image. This is going to the red. Actually, we go here to the infrared. You can clearly see the difference. Something you can notice here that there are some dark lanes in the image. If you can see the cursor, which I think so, yeah, you can see the cursor. Some dark lanes that you see better in the blue light because it's dust. This is absorbing the light from the stars, and this absorption is more effective at blue wavelengths. And this is why also the image in the infrared, which is down there, is much smoother than the images in the blue. So this we'll put it in some repository, and we'll give it to everybody, and we'll see what you can get out of them. Okay? Okay, thank you very much. So now there are many more things. I rest a little bit. I don't know. Elena is here looking at us. What can we put in In the meanwhile, we just exchange a little bit and you sit down again. What can we put down there? Some video or some presentation? Oh, okay, fantastic. Our support astronomer today.
Hola, soy Daniel Reverte, astrónomo de soporte de Gran Tecan. Y bueno, yo estudié astrofísica, hice un primer ciclo de físicas en Granada y después me licencié en La Laguna, orientación astrofísica. Después acabé haciendo la tesis doctoral en Granada, pero por en medio estuve trabajando para el Museo de la Ciencia y el Agua en Murcia, porque soy de Murcia, mi mujer también, y la mayoría de mis hijos también. Y después de la tesis vine a trabajar aquí a Gran Tecan, donde llevo 10 años trabajando para este proyecto tan chulo que espero que podáis visitar. Mi campo de investigación son los cúmulos de galaxias, la formación estelar en ese ambiente, pero ahora estoy más dedicado a los desarrollos de el flujo de información dentro de la estructura de Gran Tecan. Cómo llevar los datos de un sitio a otro, analizarlos y entregarlos ordenadamente. No tengo mucho tiempo libre, pero en mis tiempos muertos, en los ratos libres, me gusta la música, me gusta el ajedrez, pero sobre todo me gusta disfrutar de la familia. Y ahí es donde estamos.
Hola, ¿qué tal? Me llamo Raúl Domínguez, soy ingeniero de operación en Gran Telescopio Canarias. Yo nací en Madrid y estudié allí Ingeniería Técnica de Telecomunicaciones, especialidad en sistemas de telecomunicación, en la Carlos III. Y aquí en Gran Tecan pues soy responsable del mantenimiento del espejo primario y aparte de todo eso, que ya es bastante trabajo, os podéis imaginar, pues llevo el área de operación técnica en la cual pues tengo que asegurarme de que los operadores tengan las mejores herramientas posibles para poder realizar su trabajo en las mejores condiciones. En mi tiempo libre pues suelo pasar con mi familia todo lo posible, con mis 2 hijos, pues vamos a la playa ahora que empiezan las más horas de sol por la tarde, a la piscina, o tenemos una huerta en casa y dedicamos bastante tiempo a la huerta y a los animales que tenemos.
Okay, so we are here again. So thank you to Romano. Now I think he's drinking a lot of water, a poor man, because he spoke a lot. So now I'm going to talk with you. So we have a lot of questions on our online chat. So first of all, I would like to thank again all the people who is following us. And Dave, we have a question here. Can we answer it?
I think so.
Yeah. Can we read it also? Which one?
So the question is from Greg, and it says, how many bits per color, and what res are these images? So the first thing that we need to explain is that these are not color images. So the idea is that you make the color. So each of these are black and white.
Yeah.
So for each pixel, all you have is a count, and so the bits in the image is 16 bits. For each pixel, and the resolution, the images are, I think, something like 2000 by 2000 pixels, so 4 megapixels.
Right. Okay. Thank you. And by the way, the 2 interviews we have just seen were about our astronomer tonight, Daniel, and Raúl, so it's another colleague. So every week we like to introduce our team. So that's why it's a Gran Tecan team. We are very proud of all of our colleagues. So I think it's an honor for us to introduce them. Okay, so other questions? Per channel. Okay, yes, right. So I think
we're done.
We're done. Okay, so now I think we can speak about the context of the last week and then of course we can ask more questions to Dave. But I think you would like to know more about the new contest and of course the answer of the old one. So for the people who watched us last week, we had a very easy, I don't know, for me, well, not so easy, yes, but it's was about two astronauts. So we pretended to be two astronauts who wanted to measure the size of an asteroid. That asteroid, we landed, by the way, on that asteroid, so we wanted to measure the size of the asteroid, and we had a rover, 2 sticks, and a measuring tape. So was it tricky? A little bit. But our colleague Agustin made the math for us, so now we have a video explaining everything and explaining the result. And then, of course, the new contest for you, for everybody. And remember that you can participate, you can send us your answer. By the way, we have our contact methods here, so you can contact us. We have our website, of course, grantecan.es. And you can send us your answer live at gtc.iac.es. And of course, you can follow us on Facebook, Twitter, Instagram, and of course, YouTube, youtube.grantecan.es. So please send your answers to the contest at live at gtc.iac.es. And now, I think we can show you the results of the old contest. So, are you ready? Ready?
I'm ready.
Okay, good.
Hello guys, let's go with the contest results of the last week. Last week we were challenging you with the question of the situation of two astronauts in an asteroid where both of them has a stick, and try to guess the size of the asteroid by measuring the shadow casted by each of the stick. Each astronaut was 1 kilometer away from each other using the rover, so it was a very easy situation to replicate the solution of the method of Eratosthenes. Eratosthenes was a Greek guy living almost 200 years before Christus, and he was so clever that he measured the shadow of a big stone in the north of Egypt, while in the same day he knew that the sun light went straight inside a well in the south of Egypt. He knew the distance more or less. He has estimated the distance, and he was able, with these calculations, to guess the circumference length of the Earth with an error around 100 kilometers. So it was very, very surprising result so early in the history of the mankind. So this method can be simplified like with this graph. Basically, you have two sticks in our case that you ensure they are vertical with a weight hanging on a weight or whatever, and then you know the distance among the sticks. In our case, well, 1 kilometer, and the sticks height were 1 meter each. And we say that the shadow cast by the first one was 25 centimeters, and the shadow cast by the second one was 50 centimeters. So at the end of the day, you only have to use this equation. It's very easily calculate the angle of each, the angle that the shadow gets over the stick. That is using the arcotangent of the shadow over the stick height. And so the difference of the two angles happen to be exactly the angle of the arc among the two positions. So if we know theta in this case, we can use this relationship and convert it into the length of the circle, total length, dividing just in a proportion of 360 degrees for the whole circle, and theta is the arc we are trying to measure. So that was a very easy question, but we wanted you to realize that there were very clever people a long time ago. They already knew that the Earth is not flat at all. So the resulting circumference length of the Earth, in this case in our asteroid, was 28,000 meters, and the resulting diameter of the asteroid was 9 kilometers, around 9 kilometers. So there were a lot of winners, and let's try to go for them to find who is going to win the t-shirt this weekend. So, like in other events, let's use this service of random choosing of a name from a list. There are many on the internet. This is just one of them. And the winners are Javier Tapia, Antonio Marante, Jordi Marco, Carles, Juan Sisi, Josep Joan Cipi, Cristobal Gamez, and Mario Jimenez. So let's go for it. Let's go for the first winner. And the first winner is, pick one, Carles. Carles is the first one. We need 3 of them. So let's take out Carles from the list. Second winner, Javier Tapia, second winner for today. And the third winner is Jordi Marco. So we have already 3 winners for this week. Thank you very much for participating. Hope you enjoy it, and see you soon.
Okay, so we are live again, and congratulations to the 3 winners. So they will get a t-shirt with the logo of Gran Telescopio. And thank you to everyone who participated in the contest. And I would like to say that we will really appreciate that you will send us the pictures wearing the t-shirt. So you can send the picture to this email address, live@gtc.iac.es, so wearing the Gran Telescopio t-shirt. And right, so now we can introduce the new contest of this week. So it's in English. Agustin will speak in English, so you can participate, but we will unveil the answer next week. Maybe we will say that both in Spanish and English. So, right, we have a new intriguing contest, and so we encourage you to participate in all our contests, because the winners can also participate in can accumulate points, and so and the highest score will get a diploma, a Gran Telescopio diploma. So it will be a sort of a commander Gran Telescopio. So we really encourage you to participate. Okay, right, so are you ready for the new contest of this week? Are you ready, Dave?
I'm ready.
Yes, okay, so let's see.
Hi, here we are again for a new contest of GranteCan.es. Tonight, the question is, what is the height of that satellite? Probably you know that we are offering 24 hours the access to cameras that you can see the observatories from outdoors, indoors, but during the night and when the dome is open, we also offer a special camera that is called M2 mirror camera or pointing camera in the website, and you can have there the information where are Gran pointing, and also you can download that images. In fact, you can use your mouse to see which are the constellation we are watching to. So for the first step, we propose to you, you download the image. In this case, we download this specific image, and we found in this image a trail of a satellite. And the question is, can I calculate the height of the orbit of this satellite just with this? Wonderful. Yes, it's easy because I used to see the GranteCan.es live streaming. So let's go for it. The first step is just to download the image and send it to a free service like this astrometry.net. This service is quite useful because it's capable to calculate the place where you are aiming to without any further knowledge, just sending the image. And not only that, not only calculate the constellation and stars and all the object that you are aiming to, but also calculate very useful data from your pictures, like your size in the sky. So in this image, the size is 27.3 by 18.1 degrees. So it's quite wide field camera, but also it calculates the pixel scale or plate scale. That is 19.9 arcsec by pixel in this case. So with these two information, we can go further with another tool, for instance, that allow us to just measure the size of the trail. We can do it by hand, of course, but there are a free tool that's called DS9 that help you to identify the pixel by pixel and have a measurement, accurate measurements of the trail. We have done this for you, and we've discovered with this specific trail, it measured 231 pixels for an exposure time of 60 seconds that it was also provided in the original image. So we have the trail size in arc seconds, and we have the time the satellite have produced this trail. So we have everything to calculate his orbit. So Eureka! I know the height of the orbit. That is the question. Please scratch your head and try to guess using all the standard formulas to find out what is a circular orbit and try to guess what is the speed of the circular orbit, and from that deduce what is the height of this orbit. I see you in the next week.
Okay, so back again, and as I said before, we really encourage you to send your answers. So here, okay, this is our email address. And right, so a tricky question this week, right? The one of the contest, but yeah, send us your answer, and let's see in the next program. Okay, so remember for the new viewers, we say hello, welcome to all our viewers, and we are on live streaming from Gran Tecan. Okay, so you can send us all your questions about Gran Telescopio, about astronomy. Tonight we are talking about nebulae and stars and dead stars, living stars, newborn
anything.
stars, anything, and black holes. We have here Dave. Hello, Dave.
Hi again.
We introduced you before, but so here we have you again. And we'd like to talk about our cameras. So we have a live camera here. So this is our camera mounted on the secondary mirror called M2. So we can see exactly what the primary mirror sees. Okay, so it's a 50 millimeters lens pointing to the sky. So we can see it, a beautiful starry sky tonight, despite of a crescent moon. Actually, you can have access of our camera 24/7. Okay, so it's a great way to learn more about Roca de los Muchachos sky and Gran Telescopio. We can also have external camera, so it's a fisheye camera. Now we can see, yes, the globe, the fisheye camera. We can see our moon over there, so, and all the parameters here. Okay, so we have a pretty temperature of 10 degrees, but it's pretty warm right now. Yeah, we are still in winter. Actually, we are technically we are in spring, but up here temperature is still supposed to be cold, but today is quite hot up here, and a very low humidity, but it's very good for us, for astronomers, because we fight against high humidity levels. Actually, we like these values because it means we can have a very unpolluted sky. I mean, free of so water, fog, and clouds. Everything bad for astronomers. So you can also have a look at the camera anytime, okay? So through our website, grantecan.es. So now you can see the dome open, the moon. That's why we cannot see as many stars as we want. But of course, it's a crescent moon night. So you have access to all this camera. Okay, and also we can have a look from inside the dome. You can see the telescope and the open dome over there. Yes, so it's if you want to learn more about the telescope functioning, its movement a little bit slowly. Yeah, could you see it, Dave?
Yeah, it just moves.
Yes, but actually when the telescope is tracking Earth movement, you won't note the movement because it's too slow, but we can certainly perceive it when we are pointing, when we are moving from one star to another. So I like to ask to our astronomer Daniel, that is who is in the control room, what we are looking at tonight. So what do you think? Shall we call it? I think we could.
Why don't we answer the questions
Oh,
first?
yes, of course. Yeah, we have
somebody has a guess for what the cube is.
Yes.
GTC, which I guess must be Romano.
What is the cube?
Asking what is the cube. So earlier on in the broadcast,
oh yes, so
we discussed, or it was asked, what is this cube?
Oh wait a second. Sorry, because
What is this cube? And in fact, we showed the teaser. I think it's here. Is it not there?
Oh yeah,
in the teaser picture, you have Romano holding it.
It's transparent because it is.
It really is.
Yeah.
And somebody has guessed it. Somebody has guessed it is a piece of mirror.
Yes, right. So it's part of the GTC mirror, right? It is, and it's very heavy actually.
It's very heavy.
Yes, it is, because can I?
Please.
Oh my! Yeah, with this I think I can save my ticket, my bonus for the gym. Yes, it is. So congratulations. You were right, Isabel. Yes, it's part of GTC Mirror. Good. Okay, good. I'd like to speak with the astronomer. Maybe are they busy? Or we can try now. Okay, we can try and speak with the astronomer. Okay, so now we call him.
Hola.
Hello, Daniel. Hi.
Hello.
It's me
Hi.
again. So now, are you busy now? Is it a bad moment?
No, this is a good moment.
Okay, very good. So say hello to your family. Yeah, hello, Daniel, again. Could you please tell us what are you looking at right now? What are you pointing at?
Yes, sure.
Yeah.
Now we are starting with image, and here we are pointing to a field with object of interest for this technical is the multi-object spectroscopy.
Okay.
In this technique, we configure the instrument to let pass only the light of those objects we're interested in.
Mm-hmm.
We make use of some fiduciary stars to ensure we are pointing what we want, and then we set the complete instrument, and here you can see the result is the spectrum of the objects that the researcher want to analyze. Some of these spectra are coming from the stars that guarantee that the field is correct.
Yeah.
And this is it.
Okay. Yes. So as our viewers can see from the screen, actually what GTC is looking at is not a pretty image.
No,
of
not
course.
really.
Yeah. But I know. Okay, it's amazing for the astronomers, but maybe not for the general public.
So maybe we should try and explain exactly what
Yes.
the image is.
Yes, exactly.
Do you want me to try?
Yeah.
So if I
no, the pointer doesn't work right
okay.
here.
So each of the stripes that we see across is the spectrum of one star. So the spectrum is when you take the light from the star and you split it up into its composite colors. So you can see for each of those horizontal stripes, it has vertical lines in it, bright vertical lines and dark lines. So those are emission lines or absorption lines in the spectrum of the star, which can tell us information about the chemical components, whether it's got carbon or oxygen or things like that.
Yes.
In it, and also it can, based on what color it's brightest, it can tell us the temperature of the stars. So with this, we can get way more information than we could with a simple image.
Right. Actually, we know that properties of stars are related one to each other. I mean, our sun is yellow because it's a middle-aged star. Okay, pretty young, but let's say middle-aged. So it's made of hydrogen, right? So yellow color means hydrogen, in this case, basic element. But maybe if we have an older star, maybe a red giant star, or when we talk about supernova, so we'll discover other heavier elements. So it's totally different. That's why spectroscopy tells you how to find out all the properties of stars.
Exactly.
Yeah. So it's very useful for us, an astronomer. So Daniel, sorry, which is the next schedule? Okay, so the schedule for tonight.
What is the schedule? Well,
Yeah.
according to the conditions, we have, you said before, pretty good conditions. We are measuring sub-second scene,
Yeah.
and transparency is pretty good also. So we're gonna follow the instruction of the head of science,
Yeah.
and perform some pointings here to take the maximum benefit from Emir, and after midnight we will move to Osiris. Osiris is an optical instrument, and we will change in the type of science to be performed.
Okay, right. Actually, I like to say that, as we mentioned before, we have 2 instruments mounted at the Nashmit Foci. So Nashmit A comes with Emir, that's the infrared spectrograph, and Nashmit B, Osiris, or can we say Osiris? Osiris? I say Osiris, yeah. Actually,
hear something like Osiris.
yes, right. Used to call it Osiris, but it's in English tonight, so.
Yeah.
Okay, good. And actually, when we switch from one instrument to another, remember that GTC is a new generation telescope, so we can do it quickly. But actually, this is not possible with an old generation telescope. I mean, with old telescopes, this switching from one instrument to another is not possible in 5 minutes, maybe 5-6 minutes. How long does it take, the switch?
It depends on the telescope and the design, but what we can say is here is pretty quick, pretty fast, and this allow to better optimize the schedule during the night and to fit the conditions. We are following what the sky allows to observe.
Yeah.
And every facility, every is in order to get the best of the instrument.
Of course. Okay, Daniel. So thank you very much. Yeah. So have a good night.
Thank you.
And maybe let's go later. Let's go you later. Thank you very much, Daniel. Bye.
Ciao.
Bye. Okay, so let's have a look at the camera again, because I like to show to our viewers how the sky, La Palma sky, looks like. So
it looks a lot better than that, really.
Yeah. Yeah, because actually remember that we have a crescent moon, so of course it's not so dark, but okay, as we said before, just for the ones who are following us, but they were in late, so I like to show you the functioning of the telescope, because we were speaking about the foci, the instrument, but where are the instruments? So here we have, you can see the first focus, the primary focus Cassegrain, and actually we were talking about the other 2 foci, Nashmit B and Nashmit A stations. Okay, so here we have a mirror. That's it. That's a mirror spectrograph, and Osiris, right? So they are located on the two Nashmit stations because they are very heavy instruments. I don't remember exactly the weight of the instruments, but
Tons.
Tons.
Various
Yeah.
tons.
Remember that the entire structure of the telescope weighs around 400 tons. Okay, the instruments are not so
No, not quite.
not like that, but that's why we had to put them at the Nashmit stations. And then 4 other foci here, 1, 2, 3, and 4. Okay, we have Hypercam, and now next week maybe we'll have Canary Cam again. It's another infrared instrument. We had Canary Cam a few years ago, and then we'll have it again. So good. By the way, just a curious fact about Osiris. Osiris saw the first light of the telescope. The telescope was inaugurated in 2007. Okay, but the first light, actually the real first light, was in 2009. So we will celebrate 10 years this year.
And I think coincidentally, the first light image was actually of M51, which we've been imaging tonight.
I think so. I was not here, but I remember something like that. Okay, so more questions. Let's see if our any suggestion about the material. Yeah. So remember, oh my God, this one, this cube. Okay, this is a part of the mirror. It's very, very heavy. Okay, so what about?
So just to give an idea of how heavy it is, for one of the 1 meter mirrors that makes up Gran Telescopio, each of those is half a ton.
Yeah. Remember, we have 36 hexagonal mirrors. The primary mirror. So, yeah.
So you have 18 tons there already.
Yeah. Remember, so this is the primary mirror, okay? So you can have an idea of the size compared to a human person. That's the size of the mirror. Oh yeah, that's the material is it comes from Germany.
Mm-hmm.
Schott.
Manufacturer.
Yeah.
Schott.
Okay, that's it. Okay, so we have received many questions about movement of the telescope. So the functioning of the telescope. How does a telescope move and how does it work? So we had last week our engineer Luis, but we can answer. We can shortly answer to that question. Just showing you how the telescope moves. So we have 2 movements here. You can see the elevation movement. Okay, it's a very slowly movement actually. So you can see here primary mirror. Okay, and this is all the structure of the telescope. The secondary mirror is here. Size of the secondary mirror is 1.2 meters. It's made of beryllium. It's a very light material, because secondary mirror has to move very, very fast, many times per second, in order to give a perfect image of the object we are looking at. So you can see the telescope right now. just to answer to previous questions we received via email. So we are inside Gran Telescopio Canarias, but we are not in the dome. Actually, we are in a closed room, but we are not inside the dome. So this is a real video, but it's not in real time. I mean, this video was recorded, I don't know exactly when, but...
not during the night, because we
no,
don't have the lights on
course.
during the night.
Of course, and the dome is closed, so it was during the day. Why it has to move?
Because the stars aren't fixed.
All right.
You have to be able to follow the stars and to move between stars. If you want to observe one star and then another, you have to move the telescope to point.
Right. The secondary mirror.
Secondary
yeah.
mirror.
Because, you know, secondary mirror has a slightly convex shape, is smaller than the primary one. So when you have to correct certain way, you have to correct and capture the picture coming from the primary mirror. So that's why you have to move it. But actually we have to
So
answer.
it's actually to do with when you observe in the infrared, the sky is so bright that you can't stay in one place to observe your star because the image will saturate very quickly. You'll just see white light. So what you have to do is a technique called nodding or chopping, where you move the mirror very quickly to take pictures of the sky. So you move the mirror slightly, so you're moving away from your object, take a picture, move back to your object, take a picture, very, very short, and then you basically add up all of the pictures of your object and subtract away all of the pictures of the sky to get a good picture of your star.
Actually, we can see this movement here. It's the secondary mirror is moving many times per second. And actually, beryllium is a very light material, but the size of the secondary mirror is very small compared to the first one. But actually, the cost, do you know maybe the cost of that? I don't know, actually.
Much more than the primary, I would imagine. It's extremely expensive.
Yeah. So we also received a question about the total price of the telescope, because our viewers are intrigued by the price of the telescope and the cost of one night of observation. So the total cost of the telescope was around 120 million euros, take into account that the project was released in the 90s, I think. Yes, because building works started in the year 2000, but we are talking about the 19th, so for that years it's a great amount of money. So Mattia is asking if it moves as a single piece or is modular. Actually, secondary mirror is just one piece of glass. On the other hand, the primary mirror is made of 36 hexagons, so we can see them here. Okay, we can see all the 36 mirrors. Okay, and the reason why the primary mirror is by the way, is a new generation telescope, a new generation mirror. So the reason why we have to do it as a to make it as a segmented mirror is that we cannot have a monolithic mirror. We cannot have only one piece of glass of 10 meters. It's too difficult. It's too tricky. So that's why we have to make a segmented mirror. Actually, also Hawaii telescopes, the 10-meter telescopes at Hawaii have a mirror like this, but all the new generation telescopes will be built like GTC, so the big telescopes, at least so with a big segmented mirror. Right, so, okay, the other movement of the telescope, as I was mentioning before, is azimuth. So we have this movement. Here we can see primary mirror again, okay? And the telescope moves exactly like a cannon moves, you know, both on the horizontal and vertical axis. So actually you can see it's not as fast as we can see in the video, actually. It's but I think in less than 1 minute, maybe 1 minute, and yeah, can rotate. Okay, so Mattia, the same reason why I used laser pointing.
No, he's having a discussion
Yeah.
with
Yes, yeah.
I think we can leave that.
Yeah, Romano is answering the question. Okay, right, so we can see the movement here. Good. Tonight we have, as I mentioned before, a crescent moon. So that's our sky. Our sky tonight, you can see it here. Okay, and you can also check the status of our live camera 24/7. Remember our website for the ones who were not watching us before. So live cameras are at youtube.grantecan.es, live streaming, and at on grantecan.es you can see all our cameras. So, good. Let's talk a little bit about nebulae, maybe. Would you like to tell us more, or?
Well, if nobody has any questions, then I think we've covered
yeah,
enough.
I think we discussed a lot about nebulae and stars before. Oh, by the way, if you lose the previous live streaming, you can also you can watch them on our website. Okay, so we are now on the 6th live streaming. So the previous ones were in Spanish, but this is the first one in English so far. But maybe we have more streaming in English in the future. Nobody knows, maybe. Okay, so I'd like to play a very beautiful video. In my opinion, is one of the most beautiful videos we have about La Palma, because actually it shows how beautiful is our sky, unpolluted sky and dark sky. So we are very proud indeed of this place of La Palma. So yes, let's play the video, and we are back in a few minutes. Okay, so we are back again, and I hope you enjoyed the video. We have the last question about the maintenance of the mirror. How do we keep it clean? Okay, so we have a very a schedule for the cleaning up. Actually, every 3 weeks we use carbon dioxide directly on the primary mirror surface. And the great advantage of having a segmented mirror is that we can remove one little mirror in order to properly clean it, right? So we can remove a mirror, we take it to the cleaning room, we wash it using water and soap, actually with a neutral pH. Somebody told me, asked me, do you use Johnson shampoo for children? Okay, it's not the same thing, but it's actually water and soap. And of course, carbon dioxide, snow, actually clean the primary mirror in a very good way. I mean, it removes all the dust particles very quickly. Yeah, and then of course we have to replace the thin aluminum layer that reflects the light. We coat the mirror, so the coating process
So regularly the mirror is cleaned in situ on the telescope with carbon dioxide, and then every few weeks a segment is taken out and replaced with a spare segment, and in the meantime the segment is taken away, cleaned, it has the surface removed and has a new layer of aluminium placed on so that it's more reflective as it should be.
Yes.
And ready to be switched back in for the next segment.
Right. So, right. Okay, just a very curious fact about the names of the mirrors, because we have 6 segments and each segment is made of 6 mirrors. But all the mirrors, all the segments has a name of each of the Canary Islands. So there is the La Palma segment, Tenerife, Lanzarote, and so on. And then each mirror has a name of, for example, typical La Palma trees. There is a dragon, the dragon mirror, or something else, maybe food. So actually it's,
So right. As Mattia is asking, yes, so the pieces can be removed individually. So the way that the mirror is maintained in the precise shape that it is that all of the, even though it acts as one mirror, all of the mirrors are independent. And so they can all be moved independently, tipped, tilted, pushed up and down to make sure that they maintain exactly the right shape. And that means that we can also take one out. And you can also, if one were to be taken out and not replaced, you would still be able to observe and still be able to get the same picture, you just wouldn't collect as many photons.
Right, of course. Okay, so now we are close to the end of the 6th broadcast. Remember, next week we will take a break because it's Easter time. So on Saturday, 20th of April, there won't be the broadcast live streaming. So we there will be again. We'll be back in 2 weeks. So we'll be on Saturday, April the 27th. Okay, right? So, Dave, we would like to thank you.
Thank you for having me.
So, thank you very much.
Thank you for listening and for watching.
Okay, and remember, see you on April 27th. You can follow us on our GTC grantecan.es, and youtube.grantecan.es. Okay, so that's it. And now I hope you enjoyed this live streaming. Really thank all the viewers, and see you in 2 weeks. Okay, thank you very much. And remember our contest. Please answer this easy question and send your answer to our email. Okay, so thank you very much. Good night and see you in 2 weeks. Bye-bye. Bye.
Ciao.